Okay, so put away your stuff. Prepare to be bored. Yes, thank you. Okay, so just to get started, let me give you something to warm up. What is the Taylor series for natural log of 1 plus x? Okay. So I want you to take 2 minutes and write down the Taylor series for this, just to remind yourselves of what we're doing. Yeah. And please close your computers. Okay, so what do we need to do? Right? How do you find the Taylor series for this sort of thing? How do you find a Taylor series? Let's say centered at 0 again. What do you need to do? How do you find a Taylor series?
F0.
F at 0, right? So you need to say what is f at 0, right? Well, that's the natural log of 1, that's 0. What else do you need to do? You need to take derivatives, right? So let's do that first, maybe. So f of x is natural log 1 plus x. F prime x is what? 1 over 1 plus x, right? F double prime x is what? need to differentiate this. Don't tell me you forgot how to differentiate. Okay, everybody go back to calculus 1. Right, this is 1 plus x to the negative 1. Right. Negative 1 over 1 plus x squared. Right. Okay, now even harder. Take the derivative of that. What do you get? 2 over cubed, right? And so on and so forth, right? So the right the kth derivative is going to be negative 1 to the k plus 1 times k minus 1 factorial over 1 plus x to the k. Right? You keep on doing it, you see what happens, right? You get k minus 1 factorial on the top, you get this negative 1 to some power, right? And you have the 1 plus x to the k. Okay? Right? So, if you evaluate that at 0, right, you're going to get negative 1 to the k plus 1 times k minus 1 factorial. Okay, so what's the Taylor polynomial? So the Taylor series for the function is going to be summation. This thing evaluated at 0, negative 1 to the k plus 1 times k minus 1 factorial over k factorial times x to the k from k equals 0 to infinity. Right? F evaluated at the k derivative evaluated at 0 over k factorial. Right? That is, i.e., summation negative 1 to the k plus 1 over k times x to the k, k from 0. Okay. So just to remind you of what kind of game we've been playing, right? Okay. So, okay. Yeah. Oh, from k equals. Yeah, how should we write that? So the thing is that you actually do have from k equals 0 to infinity. Wait a second. Yeah, you're right. You're right. Sorry, it should be from 1. But then when x is 0, we get 0. Yeah, that's right. Sorry. Yeah, because the 0th term, the coefficient on the 0th term is 0. Right. Right. Yeah, sorry. Thank you. Okay. So okay. So let's recall some other terms. Okay. So f some function. Okay, we define this thing P sub n x is the nth Taylor polynomial. Right, the nth Taylor polynomial is going to be with sum of fk0 over k factorial x to the k from k equals 0 to n. Right. This was the nth approximation, right? Okay. And we called the difference, the error, or the difference. I'm sorry, we call this the remainder. Remainder was the function minus the nth guy, and we call this one Rn plus 1. Okay. And what we said was that we had this formula, Lagrange's formula, that said that the remainder actually turns out to be the n plus 1 derivative evaluated at some point c over n plus 1 factorial times x to the n plus 1 for some c between 0 and x. Okay, and I should say that you can also do this centered at A, right? So there's the centered at A version. What we're centered at 0. So this is the centered at 0 version, but you also have a centered at A version, right? So if you want to get the expression at some point other than 0, right? You have something like this, right? fk over k factorial x minus a to the k, right? K from 0 to n, right? And down here you would get fn plus 1 c over n plus 1 factorial x minus a to the n plus 1. But anyway, we're just, for simplicity, we're going to stick with the centered at 0. Okay. So, and then what we said was that, what we observed is that, we said, well, look, our n plus 1 x going to 0 is the same thing as saying that the limit of Pnx is f of x. Right, so let me see this. The limit of the remainder being 0 as n goes to infinity is the same thing as saying that the polynomials, the limit of the polynomials is your function. Right? Remember, this is f of x minus Pnx. Okay, so if the remainder goes to 0, that means that your polynomials come back to your function. Your polynomials come back to your function. That's the same thing as saying that summation fk0 over k factorial x to the k equals f of x when you sum from 0 to infinity. So if this happens, we say f can be expanded in a Taylor series. at x. Yeah. The way we've been speaking is the Taylor series converges back to f. Or we've also been saying the Taylor series recovers f. Okay, and this is sort of what we're hoping. Right? If you have some function, you make the Taylor series, and you're hoping that the Taylor series actually recovers your function. Right? You're hoping that the difference between your function and the Taylor polynomials becomes 0 as the polynomial, as you take more and more of the as you take higher and higher degree polynomials. Okay. Right. And last time what we saw last time that e to the x and sine x do have valid Taylor series expansions. Right? That e to the x really does equal x to the n over n factorial as n goes from 0 to infinity. That sine of x really does equal x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus, etc. Right? That these functions actually do have valid Taylor expansions. Okay. Okay. Right. Okay. And you remember? I hope you remember how we figured this out. The way we saw this was we looked at the error and saw that the error always went to 0. Do you remember this? Okay. I'm gonna say it again. Right. We looked at the error and saw that the error always went to 0. Right. Why? How did we know this? How did we know this? Let's look at e to the x. Let's look at the case of e to the x. Okay. You say, okay, well, look, the error equals e to the c over n plus 1 factorial times x to the n plus 1. Right. So the magnitude of the absolute value of the error is smaller than or equal to e to the c over n plus 1 factorial, absolute value of x to the n plus 1. And since the limit of x to the n plus 1 over n plus 1 factorial is 0, we see that the limit of the errors is 0 as n goes to infinity. Okay. And that allowed us to say that it does have a valid Taylor expansion, right? Because the error goes to 0. The difference between this and the Taylor polynomials goes to 0. Okay. And we also did that. We also did that for the sine. We also did that for the sine function. We said, oh look, when you look at the sine function, the error, we did some similar game, and we said, oh look, the error goes to 0. So the sine function does have a valid Taylor expansion. the cosine function, you get, by differentiating the sine function, term by term, you get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus, etc. You get that. You can get that by differentiating the sine function on both sides. Okay. And that is also a valid Taylor extension. So this is basically what we did last time. But any questions about it? It's pretty important, so I wanted to say it again. So the question was, how do we know if the Taylor expansion, if the Taylor series actually converges back to the function? And the answer is, you have to look at the error and show that the error goes to 0. If the error goes to 0, then you've got a good Taylor expansion. Let me make one observation here. Let me make one funny statement here. Do you remember odd functions and even functions? Do you know this term? What's an odd function? What's an even function? An even function is something like f of minus x equals f of x. Right? Even, odd. Odd means f of minus x is negative f of x. Right? You've probably seen these terms before. Right? And what's an example of an even function? Well, x squared is an even function, right? X to the 4th is an even function. Odd functions, x cubed, x to the 5th, right? These are all odd functions, right? And at that time, you probably knew that cosine, right? Cosine is an even function. And sine is an odd function. Right? And now you see that the sine has only odd powers, right? That's why it's an odd function, or that's an expression of its oddness, right? It has only odd powers. The cosine has only even powers, and it's expressible as an infinite polynomial with only even powers, right? This is expressible as an infinite polynomial with only odd powers. So, in case maybe at that time you were thinking, oh, are all even functions just things with even powers? And then somebody said, oh no, what about the cosine? But in fact, the cosine actually is something with only even powers. Anyway, okay. So let's get on to. Wait a second. Yeah. Okay, yeah. Okay. Let's get on to something kind of cool. Okay. So I had a few more sort of boring things to do, but I'm going to skip them for now, and then let's do something interesting. Okay. So infinite series, and differential equations. Okay, so this is sort of like the 19th century approach. Okay, so it's basically assume that everything is differential, everything is an infinite series, and see what happens. Okay, that's the motto. Assume everything is power series. And then see what works. Or maybe like the motto is that power series solve everything. So here is a simple example. Somebody says, I'm looking for a function that satisfies y prime minus y equals 0 and y at time 0 equals 1. Okay. So I have a differential equation, and I have a boundary condition. So I have an initial value. Okay. You say, okay, well, I don't know. You know, let's see what we can do. I'm going to assume that y is a power series. Okay. You say, okay, I'm not sure what to do here, but my motto is that power series solve everything, so I'm going to assume that this thing is a power series. Okay. I say, okay, well, in that case, y prime is going to be the sum from n equals 1 to infinity and a sub n x to the n minus 1. Right? Because when I differentiate the first guy, I get 0. Right? The 0 term vanishes, because that's constant, that vanishes. But from time 1 onwards, I'm good. I can differentiate term by term. I get n a sub n x to the n minus 1. Okay? And so the equation says y prime minus y equals 0. So that tells me that this thing, n equals 1 to infinity, n a sub n x to the n minus 1, minus a sub n x to the n from n equals 0 to infinity equals 0. Okay? Right. Okay? Everyone all right? All I put was y prime minus y. Right? Y prime minus y equals 0. That's the problem. I'm looking for y prime. I'm looking for a y that satisfies this equation. So if y is a power series, then this will be true. Okay. So then I say I am going to change the indices a little bit. I'm going to make this go from 0 to infinity. Okay. But to do that, I better make this n plus 1, and make this n plus 1, and make this n. Right? If I shift the index down, then I better shift all these n's up 1. Right? To make this the same guy. Anybody confused by that shift? Are you confused? Yes? For this one? This one I'm not shifting. I'm still going from 0 to infinity. This one is going from 0 to infinity. I would like to make this one also going from 0 to infinity. It's going from 1 to infinity. So what I do is I say, go from 0, but then I will add 1 to each of the n's to shift it back up. So I take n plus 1 here, n plus 1 here, n plus 1 minus 1 here. Okay, so you just shift everybody up and shift the index down. Okay. Okay, so now I'm going to put it together. So that tells me that summation from n equals 0 to infinity. Now that they have the same range, I can put it together. So I get n plus 1, a n plus 1 minus a sub n times x to the n equals 0. Right? I put those two things together, and I factor out the x to the n. Right? Right? I get summation n plus 1 a sub n plus 1 x to the n minus a sub n x to the n equals 0. But that's the same thing as this, right? And I factor out I distribute out the x to the n. Okay. Okay. So now, what do I have here? I have a power series that equals 0. Okay. I have a power series that equals 0 everywhere. That tells me that the coefficients must all be 0. Right? So all these guys must be 0. Right? If I have a power series, summation c sub n x to the n, and I know that that's 0 everywhere. Okay? No matter what x I put in, I get 0. No matter what x I put in, I get 0. That can only happen if all the coefficients are 0. Right? That's not, if one of the coefficients is not 0, then this is not going to happen. Right? It's not going to be 0 everywhere. Right? So what I know that for n equals 0, 1, 2, 3, etc., n plus 1, a sub n plus 1 minus a sub n is equal to 0. Right? Every one of those coefficients, right, from n equals 0 upwards, all these coefficients have to be 0. Anyone lost at this point? Anyone lost? Wangdi, you look a little confused to me. I don't know if you are. Are you confused? So the story is, right, we're trying to solve this problem. We're looking for a y that solves this. We assume y is a power series because that's our strategy at this point in history. Assume it's a power series. We want y prime minus y to be 0, so we figure out what y prime is. Y prime is this. Y prime minus y is 0. Right? We write it down. Y prime minus y is 0. And then we mess around a little bit. And we say, okay, this is what it says. Y prime minus y is 0. Right? This is it. Y prime minus y is 0. Okay. And then we say, okay, if this thing equals 0, that means that all the coefficients are 0. Right? If you have a power series, this is again a power series. This is a new power series, right? And a power series has the property that this is equal to 0 everywhere, right? For whatever x you put in, you get 0. Well, for all x, that forces all the a sub n to be 0. That forces all the a sub n to be 0. Right? So that tells me that for n equals 0, this is 0. For n equals 1, this is 0. For n equals 2, this is 0, etc., etc. And if you want me to write it out, you could say for n equals 0, what we get is that 1 times a1 minus a0 equals 0. Right? For n equals 1, what do I get? I get 2a2 minus a1 equals 0. For n equals 2, I get 3a3 minus a2 equals 0. I get 4a4 minus a3 equals 0. All those things have to equal to 0. Yeah, one thing. Yeah. From here to here?
How do you change that from n plus 1 to n, the x?
How do I go from here to here? How did I change this one into this one? Okay, so think, right? If I say summation n from n equals 1 to infinity, okay, what's that? That's going to be 1 plus 2 plus 3 plus blah, 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 right? Okay, now I'm going to rewrite that. I'm going to write this as n equals 0 to infinity, but n plus 1, right? What do I get? When n is 0, I get 1. When n is 1, I get 2. When n is 2, I get 3, etc., etc. So I haven't changed it, right? I have shifted the index down. I'm starting the index at 0 rather than at 1, but I'm shifting the terms up by 1. Okay, and that's all I'm doing here, right? I'm shifting the index, I'm starting the index one step down, but I'm moving all the indices up by 1. Okay, so that's what that is. Okay. Okay. So what do you see? You see that, well, we can work it out from here, right? So A1 equals A0. A2 equals A1 over 2. A3 equals A2 over 3, right? But A2 is A1 over 2, right? A4 is A3 over 4, but that's